All right, let's take a look at today's lesson. So, yay, we get to do fundamental theorem of calculus again, right? That's really important. I mean, it's in the name, fundamental theorem of calculus, so yay. We're actually going to work this first problem two different ways. Let's kind of focus on this. So we are given a derivative, so we're given an initial condition, and we are asked to find y of 3. That's kind of our scenario. The first technique that I'm going to do is probably the most familiar one, where we have an indefinite integral, this little guy with no bounds, and we're going to find c. We're going to do it that way. So that's probably most familiar to us. So let's kind of walk through that. All right, so y would be the antiderivative. We would do the antiderivative of this, right? So I would add 1 to 2, and I would get 3. So that gives me what, x cubed. Then I add 1 to 1, and I get 2, and divide by 2. That's what, 2x the squared minus 5x. And then there's our plus c. Yay, plus c. So then what do? We want to plug in substitute in our initial condition. So -1 equals 2 cubed plus 2 times 2 squared minus 5 times 2 plus c. Then we get to do, arithmetic, the other A word, arithmetic, which is I struggle with arithmetic. Y'all know that. So always check my arithmetic. So I actually did the arithmetic. It's like 8 plus, 8 minus 10, and I move that over, and I get c is -7. So my equation is y equals x cubed plus 2x squared minus 5x minus 7. Okay. So what do they want us to do? They want us to find the y value when x is 3. So y of 3 would be 3 cubed plus 2 times 3 squared minus 5 times 3 minus 7. Okay, so doing that fun arithmetic, we will come up with 23. So y of 3 is 23. Now that's the first technique that we could use. We could use the indefinite integral with the plus c. The second technique, using the fundamental theorem calculus, is actually, we really need to feel comfortable with this technique, and because there are many times where they kind of force us to use that, where we don't really have the opportunity to do the indefinite integral with the plus c, and I will show you why in just a moment. But let's practice it. So we're actually going to use the theorem that we learned a few lessons ago. This is a theorem. And we're going to do a definite integral. And you might think, well, how in the world am I going to figure out the bounds of the integral? What am I going to do to figure out what a and b are? And really, we don't really have a lot of choices. What we use is we use the x value of the point that we have, our initial condition. We've got to use that on the bounds. Then we also need to use the x value of the value we're trying to find. I mean, those are what we're going to put on our bounds. I would recommend that you put them in numerical order. That would just make your life easier. Do you have to? No. I just recommend that you do. So we would integrate from 2 to 3 of 3x squared plus 4x minus 5 dx, and that equals, and they're using y of, so y of 3 minus y of 2. Now what we've done is we've actually created an equation. This is the equation that we're going to solve, and we're solving it for y of 3. We want to find this value right here. So it's kind of nice that it gives us an equation to solve. Okay, so what do? Well, we would do, our antiderivative here, and we would do f of b minus f of a. We're doing a lot of this. Are y'all okay if I go just straight to, just go ahead and put what that value was? After we found the antiderivative, we did f of b minus f of a, or in other words, f of 3 minus f of 2. then we got 24. You get 24 when you do that. Equals y of 3 minus, now y of 2, they already gave us. That's negative 1. So we actually just substitute that in. And then we solve for y of 3. So y of 3 is 23. Not a surprise that it's exactly the same thing as we got using the first method. Okay. So that's how we can use the fundamental theorem to find, what are we doing? This value that we're finding, this is a function value or position value. We are finding a position value using the first derivative and an initial condition. That's the scenario, okay? So how could they force us to use that so that we couldn't use the plus c? Well, typically this happens on a calculator part. This next example basically, we can't do this without a calculator. It's not possible. And you may think, what? There are some integrals that we cannot do by hand? Yes, that is true. I know that's a terrible thing. I wish I could do all of them by hand, but I can't, some of them. So we're supposed to, again, it's kind of the same scenario where we're given a first derivative, we're given an initial condition, and we're asked to find a position value. That's kind of the same thing that we just did. But the difference is I cannot do the antiderivative of sine of x squared by hand. It is not possible. And you may think, what? Are you sure? Well, let's see. With u sub, I don't have so if you recall, this part right here is called the integrand. Right, that's the integrand. And I don't have the derivative of sine in the integrand, do I? Cosine's not there, so I can't use sine as u. If I used x squared as u, if I said u is x squared, du would be 2x dx. I don't have an x in the integrand, so I'm done. I'm pretty much done. I can't. Now, I know you can't wait. We have so many more integration techniques to learn, but even after we learn all of those, we still won't be able to integrate this. So you might think, well, how's the calculator doing it? Well, the calculator is using an approximation program to do it. It's not actually, well, it's not really like Riemann sums. It's close. Somebody programmed the calculator to be able to approximate the integral for us since we can't do it by hand. You with me? That's what happened. So yes, this is one of the rare cases. Well, I guess it's not that rare. This is one of the cases that we cannot do one by hand. That's why this kind of problem would be on a calculator section. So what do we do? Well, let's use the fundamental theorem. Need to use this x value of 1, and this x value. Those are going to go on my bounds. Again, I recommend you put them in numerical order. Okay, so we would do from 1 to 2, the integral of sine x squared dx equals. That's going to equal our fundamental theorem, f of 2 minus f of 1. Okay, so I'm going to go to my calculator, and some students were a little confused about how to put this in. You may or may not be in that camp. I'm going to go ahead and pull my calculator up so we can enter this together. So we would need to go to a calculator page. Now there's several ways to get to this I guess command. I like to go through menu calculus. That's how I typically get to places. And integral, that's how I would do it. And that pulls up like a template for us. We just need to fill in the template. So also, please note that you've got to be in radian mode. In calculus, you have to be sure you're in radian mode. Please do not leave it in degree mode. You'll get incorrect answers. So radian mode. All right, so we're going from 1 to 2. We're also, another note, please don't use these letters down here to spell out sine. The calculator will think that you're just giving it a word. It won't understand. In fact, don't really ever use these white letters in your calculations. That really is not going to help you. Okay, instead, we're going to go over here, and we're going to choose its sine of x squared. So we use the gray ones down here. Those actually are variables to the calculator. X squared, not squared squared, just squared. It's really excited, isn't it? Come on, you can do this. Let's try this again. There we go. That's all we wanted. Of x. Now, I can actually hit enter here because since there is no actual antiderivative, it's not going to be able to give us an, you know how sometimes when you hit enter you get these weird things, like really weird. Please don't give me anything really weird. Just please. This is just going to give us a decimal. Okay, let's say you don't like the number of decimals that you have. Well, all you have to do is just go highlight it and hit enter, and there's all the decimals you will ever want are right there. Okay, the calculator keeps them for us. So again, we wouldn't round to the very end. We would keep that whole number. Okay, everybody okay with the calculator input? The calculator keeps all those numbers. We don't have to write down all those numbers, but the calculator holds them and uses them to do all the calculations for us. That's why we really cannot do any intermediate rounding, none of that. Right? We can't round in the middle of our problem. We can only round at the very end. All right, so let's go back. Let's see where we are right here. So let's put in 0.494508 equals f of 2. That's what we're looking for. F of 1 was a -5. Again, we're using our calculator. So we add the 5 over, and we get, what do we get? We get, actually we're subtracting the 5 over because it's being added. We get -4.505. So that's an example of where we really have no choice but to use method 2. We have no choice because we can't actually find the antiderivative by hand. So the question here is, what if you were given f of 2 and asked to find f of 1? Would that be a problem? Would that be a problem for us? Not really, would it? Would it? I mean, wouldn't I simply just, instead of having this number, I would have had that number, and I'm going to solve? So it's okay, right? It doesn't matter which one they give us as long as they give us one of them. Okay, are we okay? Okay. So let's take a look at our next problem. Okay, so this one, we're given a graph of f prime. Okay, great. So here, I'm just going to reiterate what we've done. Here, we're given an equation. We're given an equation, an initial condition, and asked to find a position, right? That's the kind we practiced up here. This kind, we're given a graph of f prime, not an equation, but we are given an initial condition and asked to find position. So it's the same scenario, but we're given different information. Okay, so what are we going to do? Well, we're going to write an integral, because that's what we do. So let's take a look. So we want to find f of 0, and we have f of -2. So we really don't have a choice what goes on the bounds, right? And we really should do it in numeric order, and I'm going to explain why in just one moment. We're going from -2 to 0 of f prime of x dx, and that is f of 0 minus f of -2. Okay, so I'm integrating forward. I'm integrating this way. I'm going from -2 to 0. I'm going this way. So I really need to calculate this area right here and use geometry. All right, we're going to use our geometry. We're going to calculate that area. Half base times height, right? So this area turns out to be 4. Okay, so go back over here. So 4 equals f of 0 minus, let's see, f of -2 is 0. And so f of 0 is 4. So that's what we have found. Okay. So what I would like to do before we move on is I would like to explain about the integrating forward versus backward. Because really what happens, this happens to us with graphs. When we have equations, it does not matter which way we go back and forth. The equation handles it. The f of b minus, it just handles it. It's not a problem. Where it becomes a problem is when we're reading off of a first derivative graph. This is where it becomes a problem. Because if, for example, let's just go the other way. If I'm going from 0 to -2, okay, if I'm doing that, in fact, we'll just look at instead of doing that, we're just going to look at this particular integral. We'll look at the integral. If I'm going this way, if I'm going from 0 to -2 and integrating backwards, then the area is opposite of what it looks like. Okay, this area has a positive sign because it's above the x-axis. But if I'm going backwards, it's going to be opposite, and it's going to be a -4. So you might wonder why. I'm going to show you why. Remember our formula? Remember the formula. So if I wanted to switch this order, what would I do? If I wanted to switch the order of these, what would I do? I would do the negative one, right? Negative integral -2 to 0 of f prime of x dx. And that would give me a -4, which is a +4. Okay, so do we understand that? That's why when we go backwards, it's opposite. Please just be aware of that. And it really only affects us, again, like I said, when we have a graph like this. When we have a graph like this, if we integrate backwards, we need to visually think to ourselves whether we would opposite, right? If I'm integrating from, let's say, here backwards, that's 6. If I'm going from 6 to 2, then that's actually going to be a positive area, right? You with me? It's always backwards if you're going backwards. So I don't suggest you going backwards, really. When we have graphs, it's easier to go forwards when you have a graph. Okay? So there's my caution. All right. So this is just what if backwards. This is us looking at what happens if we integrate backwards with the graph. Backwards with the graph is, we need to be very careful of. Okay, so let's go back about our business and let's actually find f of 2. Now, I hate to break it to you, but we always have to write the integral. Always. You get points for writing the integral. Write the integral. Now, I need to end at 2, but now I actually have a choice of where I start. I could start my integration at -2 or 0 because I was given -2 and now I have 0. I could pick either one. And I will tell you that I like to keep the area as small as possible. So what I would typically do, which I'm going to do, is I'm going to go from 0 to 2 instead of from -2 to 2. I'm going to shorten the amount that I have to calculate or do area for. I'm going to go from 0 to 2 of f prime of x dx, and that is f of 2 minus f of 0. So again, we're integrating forward. So I want this area right here, which, happens to be 4 also. So 4 equals f of 2. We don't know. That's what we want to know. Minus f of 0, we calculated in the previous part to be 4. Okay, so in this instance, f of 2 is going to be 8. Okay, so now I have that value. Yeah, so the danger is, that's the danger, is if you got the wrong value of f of 0, and then you used it and you compounded the problem twice, really it depends on how they decide to score, whether it's called read with you or not, whether we would read with you or not. It depends. It would depend on the question. So I can't really give you a definitive answer on that. So if you're concerned that that might not be correct, then it's probably safer to go back and start at -2. The issue, though, is you still got to calculate that area again. You know what I mean? So I don't know. You just need to be, I guess, careful. Area. Careful, right? Careful. Okay, so do you think I'm going to have to write an integral on part C? There's only one correct answer. Yes. Yes, I do. Yes, I do. I need to end up at 6. Okay, I need to end up at 6. Do you think I'm going to want to start at -2? I got 3 choices now. I can start at -2, 0, or 2. I'm going to pick 2. I'm going to pick 2. I'm going to count on the fact that those values are correct. Hope that they're correct, right? F prime of x dx is f of 6 minus f of 2. Okay, so again, we're going forward. Since we're going forward, what do we know about this area right here? Is it going to have a positive sign or a negative sign? It's going to have a negative sign. And it's a semicircle. So we've got to use our formula, right, from geometry. Is it half pi r squared? See, what is r? R is what? 2 squared. So looks like 2 pi to me. So -2 pi equals f of 6 minus, and f of 2 is 8. So f of 6 is -2 pi plus 8. Okay, so those are our values. And our first experience with calculating, so this is kind of cool actually. We found position values using the graph of a first derivative. We never would have been able to do this before now, right? We found position values using the graph of the first derivative. All right, so let's take a look at our next problem. Another graph. So we've got some experience with graphs now. Okay, we've got some experience. So kind of notice how they just tell us what the area of each of those little spots is. Notice how they're not giving us a sign. Why do you think they're not giving us signs? I mean, they don't know whether we're going to integrate forward or backwards, do they? No. So there's no, we don't know. It depends on which way we're integrating, whether it's going to be positive or negative. I plan on integrating forward. I don't know about y'all, but I want to integrate forward. And so if I integrate forward, then this area would be positive, right? If I'm integrating forward, which I'm planning on doing. This area would be negative, and this area would be positive. That's what we would have. Okay? So now let's look. Okay, we've got, this is f prime. We're just going to write f prime. It says f prime is shown. Use the figure and the fact that, here's our initial condition, to find f of 0. Do you think we're going to have to write an integral? Yes. Yes, we will. Okay, so please be sure. So we're integrating from, let's see, what are our x's? We got 0 and a 3. Again, I recommend you put them in numeric order. So let's go from 0 to 3 of f prime of x dx, and that is f of 3 minus f of 0. So let's look between 0 and 3. They say the area is 4. So 4 is f of 3. Oops, we know f of 3, don't we? 4 is 5 minus f of 0. So f of 0 is, let's see, what's that going to be? So 1. So that's 1. Okay, so getting comfortable? We okay? Okay. And I don't need to ask you, do we need to write the integral, right? We already know the answer to that question? The answer is yes. I am going to end up at 7. I have two choices now. I could start at 0 or start at 3. Which one do you think I'm going to pick? I'm going to pick 3 because I'm going to try to make the location that I'm calculating area for as small as possible, just because numbers are not necessarily my friend. We're going from 3 to 7 of f prime. We're integrating f prime of x dx, and that gives us f of 7 minus f of 3. Let's see, now I'm integrating forward, so am I going to have my area as 9 or negative 9? I'm going to have it as negative 9. That's negative 9 equals f of 7, which we don't know. F of 3, they actually told us, was 5. So f of 7 is what, negative 4? Check my arithmetic, is that right? Okay, good. Good. All right, one more. Let's see, I need to know the function value at 9, the position value. I'm going to go from 7. Y'all okay with that? I'm going to go from the integral from 7 to 9 of f prime of x dx. So that's going to be f of 9 minus f of 7. Let's see, as I am going forward, that's positive area, so that's 2 equals f of 9 minus, what was negative? It was negative 4, wasn't it? Negative 4. Okay, so f of 9 is, so that's negative, that's a positive 4, so I subtract, so that's negative 2, right? Okay, good. Now they want us to sketch the graph of the position of f. Well, okay, we could do that. All right, well, we've got 4 points. Now, let's plot those points. So we've got f of 0 equals 1, so we've got that. We've got, what do we know? F of 3 is 5. 1, 2, 3, 4, 5. So we've got that. What do we know? F of 7, 1, 2, is negative 4. Okay. And f of 9 is negative 2. Now, we really don't know what's going on. I mean, we would like it to be, like this, right? We would like that. But does it have to look like that? No. I mean, it could go like this. I mean, right? We don't know what it looks like. So what are we going to have to do to check it out? We're going to have to look at the first derivative. We have to figure out what to do. So we've done this before, and I recommend that you do a sign chart for the first derivative. So this is f prime's sign chart. Okay, and again, we're going forward. Okay, well, we're doing the sign chart of the derivative. So this is above the x-axis, below the x-axis, above the x-axis. Okay, so first derivative test for a relative extrema, we have that in our brains, right? Okay, so first derivative test for relative extrema, what do I have going on right here at 3? I have a relative maximum, don't I? I should have a relative max at 3. What do I have going on at 7? A relative min. Do I have any other relative extremas between 0 and 9? No. And how do we know for sure? Because there's no other critical numbers, right? If you recall that the theorem tells us that relative extrema occur when the test tells us relative extrema occur when the first derivative changes signs. So we're kind of safe right here. We can just do there's a maximum. That looks pretty good as a maximum, don't y'all think, at 3? There's a maximum there. That's a pretty good, that's the value at 3, so that's the maximum. And then we actually have the y value at 7, so we're really in good shape. I mean, that our graph does look like we thought it would have looked. We just can't trust that. Does that make sense? We can't trust it until we check what the actual first derivative is doing. Okay?